They plan was to knock me out the top of the game, but I overstand they truth is all lame. I hold cannons that shoot balls of flame, right in they fat mouth, then I carve my name.
So, knowing these addition and subtraction identities also allows us to kind of, in a way, like break up sine functions and break up cosine functions, or put them back together as well. Okay, so what do I mean by this? Let's say we have some function, f of x, is equal to, I don't know, a times sine of bx plus c. Okay, let's say we just have something of this form, right? We're given some function like this, okay? So the thing is, because we know an addition identity for sine, we could break this up into sine of bx times, well, and I should write a parentheses here, cosine of c. So this is kind of like our bx is kind of like alpha, and c is kind of like beta in the formulas that I listed in the very beginning. Okay, and then we have sine, so that means same sign in the middle. Okay, and then we just switch the values. So sine of c times cosine of bx. Okay, and then from here, I'm just going to distribute the a inside, just for the heck of it. A is just a constant, as are b and c. Okay, so we could get a, and then I'm just going to switch a couple things around. I'll just switch the order. So cosine of c times sine of bx plus, and like I said, I'm distributing the a in, so get a times sine of c times cosine of bx. Okay? So the thing is, why did I do that? That's really weird. But basically, what we can do from here is that because we went this way and just disassembled, kind of, we just decomposed this sine function here, right, using the sum of, or the addition identity for sine, right? So we broke it up into two pieces separated by a plus sign. We can do the same exact thing and take something of this form and bring it back and kind of consolidate it and squish it back into one sine graph, or one sine function, or we could do the same thing with cosine as well. But anyways, so the thing to note here is that let's say we were given, okay, so on a different note, let's say we're given a function like this, m, which is just a constant, times sine of bx, okay, plus n, which again is just a constant, like a number, times cosine of bx. So if we have the same period, which is determined by our b, by the coefficient, so this, our period would be t is equal to 2 pi over b, like we've learned in previous sections. T is equal to 2 pi over b, right? So we have the same period. So let me write a little note here. If our sine and cosine, the ones being added, have the same period, or they could also be subtracted as well. It's kind of just general. If they have the same period, we can look back at our previous result, aka the one up here, right? And we can say, okay, we can actually match these up because the coefficient for our sine is right here on the bottom one, right? The coefficient for our sine on this one is right here. And you might be thinking, wait, there's a cosine in front. But the thing is that c is a constant, okay? That's just a number. So when you take the cosine of a constant, you just get a constant. So this whole thing right here, that's a constant, okay? As is this thing in front of the cosine, a times sine of c is just a constant as well, as is this n in front. So we can kind of match them up. These are the coefficients on sine, and these are the coefficients on cosine, okay? So let me write our findings on the next slide. So if we match them up, we have something like this. A times cosine of c times sine of bx plus a times sine of c times cosine of bx. Okay, so we're just going to match these up. This is going to be equal to our m, and this thing is going to be equal to our n. And they're just numbers, okay? So if we write m is equal to a cosine of c, and n is equal to a sine of c, we can work with this because we know m and n, because those would have been our givens, okay? So I'll just write a little note. We know m and n, okay? We already know these guys. So to figure out a and c, what are our amplitude and what's our c? That's just kind of a random thing. We could say, well, let's try to play around with this a little bit. So what if we do m squared plus n squared? Okay, And this is a little bit kind of spontaneous, but let's just try it. So that would be a times cosine c quantity squared plus a times sine c quantity squared. So this is going to give us a squared times cosine squared of c plus a squared times sine squared of c. We can factor out that a squared here. So a squared times cosine squared c plus sine squared c, and this here is the Pythagorean identity, so this goes to 1. Alrighty? So we have something that looks like this. M squared plus n squared is equal to a squared. Okay? So basically we can find our amplitude just by knowing m and n. Okay? An amplitude is equal to the square root of m squared plus n squared. Okay? So that takes care of a. Good on that. Now let's figure out what our c is. Let's do that on the next slide. So we have the following relations. M is equal to a cosine of c, and n is equal to a sine of c. Okay, let's just divide by a for both of these equations. So we have cosine of c should be equal to m, which we know, over a, which we now know, right? Which we can figure out by squaring m and n, adding them and taking the square root. So this one over here, this one becomes n over a. So our goal for this one is just to find something that satisfies some angle c. So from here we just find some angle c that satisfies, so fits both of these equations at the same time. Okay? Alrighty, so that might have been a lot. So this is how you would solve for C, okay, after you figure out A. Alrighty, so let's try an example of this whole process. Alright, so we're given the following problem to rewrite this thing as a single sinusoidal function, okay? And again, sinusoidal just refers to sine or cosine. Okay, so let's look at what we have. So we have 4 times radical 3 times sine of 2x, and then I'm just going to rewrite this as plus a negative 4 times cosine of 2x. So the first thing we note is that our sine and cosine, each of these portions, have the same period because we have the same b, right? So b is equal to 2, so that means that our period, which we don't really need to know at this point, but our period is going to be of pi, right? And it's the same for both. That's the important part. Period is the same for both. So what we can do is kind of consider these. This is like our m, like we were saying before, and the coefficient of cosine is like our n, okay? So with our m and n, we can figure out automatically what is our a, our amplitude. This is going to be the square root of m squared plus n squared, okay? So when we plug in m and n, we're going to get square root of 4 radical 3 squared plus 4 squared, okay? And this is going to give us 16 times 3, so 16 times 3 plus a 16. So that's basically 16 times 4, so that would be a 64 inside the square root. So our a, our amplitude, is equal to 8, okay? And just keep this in mind, our goal is to write this as a single sinusoidal function. So our goal is ultimately going to be getting a times sine of bx plus c. Okay, we already know our b. Our b was already there to start with. B equals 2. We know our a now, that's 8. And now our last task is to figure out what is c, okay? So we should now use the knowledge that we have that m should be equal to a cosine of c due to a derivation that we had before of expanding out the addition identity for the sine, right? And our n should be equal to a times sine of c. And if you ever forget, you can always just say, okay, so m, the first thing on the sine, the coefficient of our sine, should be a times something, and you know it shouldn't be the same. It should be the opposite one, so cosine here. And n, which is the coefficient of cosine, that should be the opposite, so a times sine instead, okay? And now we're going to find, okay, so cosine c should be equal to m over a, and m was 4 radical 3, and a is 8, so we need to find radical 3 over 2. We need to solve for cosine of that. Okay, and then let's work with the sine. Sine of c should be equal to n over a, which is equal to, let's see, what is n? Negative 4 over 8. So this will be negative 1 over 2. So let's continue this problem on the next slide. So we've gotten to a point where we can say cosine c is equal to radical 3 over 2. That's a positive one. And sine of c should be equal to negative 1 over 2. So now our goal is just to find a point on the unit circle which satisfies both of these equations at the same time. Okay? So cosine of c being positive, radical 3 over 2, puts us on this line. So it could be either this angle or this angle. And then we say, okay, so sine has to be negative, so that means we have to pick this angle down here, okay? And that occurs at 11 pi over 6, so that means that c is going to be 11 pi over 6. Alrighty? So now we know our a, which is 8, we know our b, which is 2, and our c is equal to 11 pi over 6, so we're just going to plug everything in so we can condense. I'm just writing down the original equation that we were given, or the original expression for our function, right? So 4 times radical 3 sine of 2x minus 4 cosine of 2x can be condensed into something of the form a times sine of bx plus c. And we're just going to plug in all of these values in order to get 8 times sine of 2x and then plus 11 pi over 6. Okay? And that looks a lot nicer, right? Because we've just consolidated all of that messiness into one single expression. Alrighty, so that concludes our concepts video on addition and subtraction identities. I hope that helps, and I'll talk to you in the practice problems video if you watch.
Oh, 56, nigga, shut the fuck up. Fuck that nigga, run that back. Money.
Run that back, man.
What?
I gotta get out, man. You gotta
run it back. Run it back? Alright, run it back.